So, without further ado.
All these are kind of like that. They're all worn out.
I'm short and I can't touch the ground with my feet anyways. Like I'm always like not moving on the ground, so it's just like I'm grabbing up by my toes and like trying to pull myself in.
Yeah.
It was a struggle. It was a struggle. It was a struggle.
So, last time we took a look at the hydrodynamic or the momentum considerations associated with flow inside of tubes. Today we're going to take a look at thermal considerations. So let's take a tube. And there'll be some fluid entering the tube at T initial. And like our case last lesson, the boundary layer, in this case the thermal boundary layer, grows from the entrance of the tube until finally it becomes of adequate thickness so that it meets the boundary layer growing from all around the tube. At that point, the flow is considered fully developed. This distance is known as XFD sub T, or the distance, the entry region or entry length for thermal effects. So it's the thermal entry length. It can be considerable. Now, as the fluid flows in the tube, assuming for a moment that this fluid tube temperature is hotter than the fluid temperature, what you're going to see is in the entry region a temperature profile of this nature. It'll look something like this. So this is where T is equal to a function of X and R. We'll talk a lot about this in just a moment. Once we reach the fully developed region, the temperature profile looks like this. And this, of course, is the case. This is a case where the tube surface is hotter than the fluid surface. Okay? So that's what we're dealing with right here, and what we're going to try to be. We're going to try to find several things that we need to solve for in order to ultimately get to what we're looking for always in heat transfer, which is ability to fix the temperature as well as the amount of heat transfer which occurs. All right. Some entry-length considerations for you to think about. We now have actually 4 different entry lengths that you have been exposed to. In the hydrodynamic regime, we have the entry length for laminar flow, we have the entry length for turbulent flow. we have the same thing in the thermal regime. The entry length for the thermal entry length for laminar flow and the thermal entry length for turbulent flow. Can we compare these? And the answer is yes. And it's kind of interesting, actually. If the Prandtl number is approximately equal to 1, then nu is approximately equal to alpha, meaning that the thermal and the hydrodynamic effects are approximately the same, and the hydrodynamic entry length will be approximately the same length as the thermal entry length. If the Prandtl number, on the other hand, is greater than 1, then nu is greater than alpha, and the hydrodynamic effects develop quicker, so the hydrodynamic entry length turns out to be less than the thermal entry length. And conversely, if the Prandtl number is less than 1, that means that nu is less than alpha, or the hydrodynamic effects are less than the thermal effects. So in that case, the hydrodynamic entry length takes longer to develop completely. And so the entry length for the hydrodynamic case effects is greater than the entry length for the thermal effects. All right, where are we all going with all of this? Well, let's just take a step back for a moment and sort of review that. We're looking at heat transfer in tubes. Now, I've already said that T is a function of both X and R. And why is that? Because T continues to change. T of the fluid continues to change as you move down the pipe. And so that poses, unlike the velocity profile, once you get into the fully developed region, the velocity profile stays the same. Okay? In other words, the velocity doesn't change. Axially, it'll only change radially. That's not true for temperature. So that poses some interesting issues for us. We're going to be looking for the heat transfer, Q of S. How much heat transfer is transferred at the surface? So we'd like to find the H. We're always looking for the H value in the convection block, times the area of the surface, times the temperature of the surface, minus the medium temperature of the fluid. Now, the reason we say that is because we need to take into consideration that the temperature of the fluid at any point down the tube is not uniform across the surface. It changes. Obviously, the fluid in contact with the edges, got to keep in mind this is a three-dimensional representation. The fluid in contact with the edges is going to be hotter, and then that heat transfer is going to increase. And it's going to heat the fluid as it moves down towards the core. The center is flowing in the center. The fluid, which is flowing in the center. But it's going to always be kind of lagging behind. So what we'd like to find for the heat transfer is what's that medium temperature? Where's the medium temperature in there? That's at Tm. And we know that area of the surface is going to be 2 pi times r sub 0, where this is r sub 0 times the length of the tube. All right, so let's keep this in mind for a second. What are we looking for here? We're looking for a way to solve for that, but even when we have that, we also need to know this, okay? We're going to do this right. All right, so let's look at the mean temperature. Now this is analogous. You're welcome to come on in there, Professor Regamani.
We just finished to do something similar on fluid.
Yeah.
So this is why I looked.
Yeah, we're right in the midst of doing very similar things with wet fluids.
Sorry, I'm waiting for his.
We just did mean velocity on, what's today, Wednesday? So Monday we did mean velocity. Does it get any better?
Yes.
All right. So anyway, now I've completely forgot what I was going to say. All right, what am I going to say? All right, we need to find this mean temperature. We need to come up with an expression for mean temperature. All right. So if we look at the thermal energy rate, which is flowing down the tube, we know it's going to be equal to the mass flow rate of the fluid times C sub P times T mean. So if I wanted to look at a differential portion or a chunk of fluid right here in this tube, I could look at what this mean temperature is right here, multiply it times Cp and M, the mass flow rate, and I could come up with the figures of that. If I wanted to integrate this, I would say this is equal to the integral over the entire cross-sectional area of the tube, and it would be equal to rho u Cp times the temperature times that differential cross-sectional area. So, I can then, let me write this. Let me now substitute in for what we know for m dot. We know that m dot is equal to the mean velocity. That's m dot is equal to rho u times the area through which it's flowing. So that would be um times times rho times the cross-sectional area, which would be pi r0 squared times Cp times Tm. And over here, I'm going to integrate this from 0 to r sub 0, so I'm going to have to get rid of the cross-sectional area or express it in terms of radius. And this would be rho u Cp times T, and a cross-sectional area would be the same as a cross-sectional radius, or portion of the radius times the total, so the total area, which is going to be, 2 pi r dr. I'm sorry, Scott? Oh. All right. All right, so we can identify this as m dot, okay? And this is dAc. And now we can come up with an expression for the mean temperature. So the mean temperature, that is this line right here, if this is my temperature profile, that's probably a pretty good approximation of the mean temperature. All right, what is that? Well, that's going to be equal to 2 over r sub 0 squared times the integral from 0 to r sub 0 of u t r dr. And this is equation 826. So let's pause for a moment. Think, yes, Megan.
So this is the mean temperature for either fully developed or
This is
non-fully
fully
developed?
developed,
Only
This is
fully
fully
developed. Thank you.
not the entry line. We're going to deal with that, not today actually, but we're going to deal with that. But whole different ballgame in the internet.
Okay, thank you.
All right. So, what do we have here? Well, we have the mean velocity, which we learned how to solve for last time. Okay. We have the radius of the tube itself. That's either given or something you would be able to measure. And then we have this value u. Now u, if you will recall, we solved for last time, and that's a function of r. T can be a function of x and r, but we're integrating it with respect to r. Okay? Because t can change. One of the cases, and does change. And then r is just the radius. So you have to integrate it with respect to this. You get to do this tonight. All right. And it does work. I did it last night. And don't make the mistake I did, which is get very frustrated myself rather late at night why my numbers wouldn't work out. And that was because I integrated this expression, but guess what I forgot to put in? The r. And it doesn't work if you don't put the r in, okay? R, yes, yes.
That R in the integral is the same as R naught?
This r? No, r is a variable. R is the position, is the variable which ranges between 0 and r sub 0.
Oh.
So r tells you where you are radially in the tube. All right, that's what r represents. It's like x represents some distance down the tube. R represents where you are radially in the tube. Okay? All right. All right. Now, I have been very, very bad in passing out the timesheet. So today I have to pass out the timesheet for 3 days. So I have added notes to the timesheet. This was for the Wednesday before Easter. Now I know that many of you won't be able to think back that far, but try, all right? So that was, how much work did you put in preparing for that lesson before you left for the Easter weekend break? Okay? Then there was Monday of this week, and that column is labeled Monday. All right. And then there is today, and I have labeled that column today. Don't screw it up. Sorry. And why didn't we have so many people absent? 5, 11, 14, 15, 20, 22, 23, 24, 25. Who's missing? Hold on, who's sitting between you two guys? Oh, okay. Plaster's mixing, and who else? Nobody else sits here? Oh, and Louis back here. Okay. Medina? Medina, you here, right? Okay. All right. So, now, let's I had a lot of fun coming up with last night's homework. Really did. Until I couldn't get it to work out. And the reason I know I couldn't get it to work out, because it's a long integral and you get all these terms and it's really ugly, is because when you work it out and you do the integral, mathematically you get the same answer as you get when you do the spreadsheet. Okay? And you notice part 1 is to work all the math. Part 2 is to do the spreadsheet. Bing, bada, boom. It actually matches. Very nice. All right. So, I thought this has got to match. It should match. And it does match when you actually include the R. Okay. So, we're looking now at thermally fully developed flow. Okay. The thing about thermally fully developed flow is that the temperature, T, continues to change we're talking about the T of the fluid continues to change with X. In other words, it never reaches dt dx being equal to 0. If you think about it, it makes sense. We're going to look at two cases here in just a moment. I'll give you an insight of what those are. The one case is where you have a constant surface temperature. All right? In other words, the tube surface is always the same. Okay? Good example of that are condensing and boiling processes. The other is where you have constant surface heat flux on the tube, so that the tube surface temperature itself continues to change. All right? So it increases. In either case, the fluid flowing through the tube is constantly going to be getting hotter, assuming the surface of the tube is hotter. It's constantly going to be picking up heat as it moves through the tube. So it never reaches this point right here. It constantly changes.
So
what-
what reach the tube's temperature?
Well, if the tube were infinite, it would approach it. If the tube temperature was constant, if Ts was constant, long enough, it would reach it. It would approach it. If, on the other hand, it's a constant surface heat flux, it's never going to reach it. I'll show you why. All right. So we define theta as being equal to the temperature of the surface minus T over the temperature of the surface minus T of M. Okay? And we're going to define partial with respect to x of theta. And it's Ts, which is a function of s, minus Ts, a minus of x, function of x, minus T, which is a function of x and r, over Ts, function of x, minus Tm, which is a function of x. And we're going to look at this in the thermally fully developed region. And the result, if we do that, is that this difference with respect to x becomes equal to 0. What this physically means is that while the temperatures all change, what does remain constant in the fully developed region? Scott?
The profile?
Thank you. The profile. So in other words, they heat up. The profile is going to remain in constant shape. All right. So this is equation 828 in your reading this thing. And we can take this one step further. And we're going to come back to this for a moment, in a moment. Partial, if we take this with respect to r of the same thing, again, in the thermally fully developed region, turns out to be equal to minus partial of T with respect to r times, or not times, minus T with respect to r in the fully developed region over Ts minus Tm. And this turns out to be not a function of x, even though T is a function of x. because the profile remains the same. This is, well, this is in your book as well, I can't read the written information. Now, notice it's a little confusing at this point, so we're going to take a moment, we're going to step back, I'm going to show you what we're going to do with this. This is particularly interesting, because now we're going to put this into the energy balance envelope. You've seen this before, of course, and that is where the conduction, which comes out of the surface of the tube, has to be equal to the convection that occurs into the fluid. But with some very specific rules. The conduction is going to be equal to minus K, partial of T with respect to R, evaluated at R equal R sub 0. In other words, at the surface of the pipe. And this convection is going to be equal to H times T of the surface minus the mean temperature. The heat transfer to the tubes equation we wrote over there, although this is in flux rather than a total heat transfer. So, H over K is equal to minus the partial of T with respect to R, evaluated at R equals 0, over Ts minus Tm. This is not equal to a function of x. And the result is that H, for fully developed laminar tube flow, thermally fully developed laminar tube flow, is equal to a constant. Now, just telling you that right now, guess what we're going to do in next lesson? We're going to solve that, okay? And to do that, we need U, and we need T, okay? We need U, and we need T. So this is the result that we're going to be looking for to show that this is the case for fully developed laminar fluid. Alrighty. So let's take a look at the two surface conditions. Which we're going to do. Okay, case number 1. Is where we have a QS being equal to a constant. Some examples of that would be solar collector, a nuclear reactor, maybe the other. Okay, where we're bombarding, if you will, the outside of the tube with some constant surface flux. And a collector, you don't see too many hydronic collectors anymore, but occasionally you do. The heat, hot water. You see them in some parts of the world. They have a lot of them. They use those a lot. And basically, what they are is they look like a photovoltaic collector, except they have a pipe that's typically painted black that circulates back and forth, and as the water flows through there, it heats up. Okay, and that would be the case 1 of a constant surface flux. Now, obviously, the sun is not entirely constant. Actually, the sun is constant. what sunlight strikes the Earth's surface at any given point in time. Case number 2 is where we have the temperature of the surface being equal to a constant. Examples of that are a boiler and condenser. Where we have a phase change going on with the fluid on the other side, giving up or receiving heat, and the result is that the surface of the tube itself remains more or less constant. So those are the 2 cases that we're going to be dealing with here. All right? So let's take a look at case number 1 first of all, which is constant surface heat flux. Okay. All right, in the case, now let me draw this first. All right, this is our temperature scale, and this is x, the distance axially down the tube. All right, and I'm going to sketch this region in here, and this equals x FD thermal. So that's my entry region. Okay, from 0, beginning of the tube, to this point is my entry region. So strange things happen in the entry region, believe me. All right. Now, in this particular case, the temperature, the change of temperature in the thermally fully developed region with respect to x, and it's not equal to 0, it changes all the time, okay? It's constantly increasing, is going to be equal to the actual change in the mean temperature with respect to x. And that will be equal to the change of the surface temperature with respect to x. And this turns out to be a constant. And that makes sense if you think about it. And it turns out not to be equal to a function of x. So, what does that graphically look like? It looks like this. What we have is, this is the surface temperature. Okay? And the surface temperature is going to be equal to a function of x. In other words, it's going to change. Oh, and the fluid temperature itself is going to look something like this. And this is going to be my mean temperature. And for this case, once we enter the fully developed region, this delta of Ts minus Tm becomes a constant. And by the way, these are equations 830 and 832 in your textbook. So what happens physically when you have a constant surface flux condition is that in the entry region, you're reaching steady state essentially, okay? And then once you reach that steady state, the temperature here of the surface will continue to change. It will continue to increase, assuming it's being heated, okay? Cool. But the medium temperature of the fluid, which is exposed to it, changes as well, but the rate at which that changes matches the rate at which the surface temperature changes. In other words, the fluid absorbs heat at a what? Constant. Okay? Once you're in the fully developed region, which is nice to know. Okay, so that's case number 1. Case number 2 is a little more challenging mathematically.
So is this true for laminar and turbulent flows?
This is true for the laminar flow.
Okay.
Turbulent flow, no. All bets are off. And everything which we're doing here today is laminar. Everything is laminar flow. We can't, for example, the equation 826 over there, that describes laminar flow. A lot of assumptions that went into this, which you kind of forget because of the length of all of this. But remember that laminar flow, we're assuming the V component is equal to 0, that du dx doesn't change, and that's just not true in turbulent flow. So how do we deal with turbulent flow?
Empirical models.
That's exactly right. And so take a look, open your books to table 8.4. Table 8.4, since you asked the question. It's on page 536. And to give you just a little hint of what's coming, look, it's the same sort of arrangement that we had in external flow. At external flow, in table 7.7, we had the laminar flow results at the top of the table, and those came out of the Blasius solution, which was an exact analytical solution, and then everything as we moved down was a result of empirical correlations. What we see here at the top are laminar fully developed, and you see the number there, Nusselt number for laminar fully developed uniform QS equal to 4.36, and laminar fully developed uniform TS, Nusselt number equal to 3.66. Okay? That is the results that we're going to obtain here next lesson. Okay? Mathematically. But it doesn't apply for turbulent flow. So what are we going to do? If you look down, what do we have? Oh, we have, and then you see some very ugly looking equations in the mid part of that table, and what are those for?
Equation for the friction factor?
Those are for the entry lengths. Those are for the entry lengths. And they're just, it's just ugly, ugly, ugly. Okay? And I've used those equations trying to get results on a laboratory experiment which we're going to do towards the end of the course. And it'll work with the darn. And basically, from what I've been able to read and discover on my own, you just want to stay out of the entry region. You know? And you can shrink the entry region a lot by doing what? What causes the entry level to entry region to shrink quickly?
Decrease flow rate.
What?
Decrease flow rate.
Increase the flow rate. Yeah, because then everything is coming together quicker. The quicker you do the flow rate, the more fluid you put through, the boundary layers grow quicker, but it's not laminar, it's turbulent. Okay? It goes turbulent. As a matter of fact, it goes turbulent very, very quickly. Very quickly.
You get more heat transfer through turbulent flow
Yes.
because there's more mixing?
Yes. Yeah. So you have not only conduction occurring, but you have the advection effects as well, the mixing. So absolutely. But, and the other thing is, in real life, nobody builds anything that's laminar. Why?
More friction.
No, I don't think it, I should say, it's not more friction, it's the other way around. But why?
Laminar's so hard to keep it around.
Laminar flow is so slow that it's to get a certain flow rate, you want an m dot, right? What do you have to do if you get laminar flow?
Have a giant pipe,
Exactly. And giant pipes cost
giant money.
giant money, so, well, that's, all right, but it does kind of have a ring to it. The bottom line is when you're actually designing something, you're going to have, nobody does designs it. I should have said nobody. I'm sure there are applications I'm not familiar with where you want to have laminar flow. But in reality, for most industrial type of processes, actual processes, you have turbulent flow. In your homework tonight, your mean velocity, I had to take it down to go lambda, so it actually worked with all the equations, down to about 0.1 meter per second, okay? That's nothing. Most flow in pipes in your house, what is the water designed for to flow? What speed in your pipes in your house?
8 gallons per minute.
That's a volumetric flow rate. What's the speed? Anybody know? About 6 feet per second. That's what water flows in your pipes. Somewhere between 1.5 and 2 meters per second. So that's a whole lot faster than 0.1 for the pipe that in your home.
So is this like non-invasive then?
Oh, there's nothing daring in this course. It's not.
Yeah. Well, like, just like compared to like, if what we're.
What you're doing is you're seeing, what I'm presenting here for you is a theoretical background for the internal flow. And we're going to actually, if I stop talking, we're going to get into it today. We'll finish this up. This is leading into the analytical solution, which I'm going to present next time in class. In other words, we're going to come up with a Nusselt number of 3.66. We're going to do it by using the value for U as a function of R that we came up with in the last class, and the mean temperature equation, which you see right there. And if we do that, we can come up with the value they have in the table. All right. And your homework, you're actually going to integrate T in. And as long as you remember to put the R in it, you will get the right answer. All right, quickly then. The last case, and then I want to talk a moment about your homework, because again, we'll draw our graph. Again, we'll put in the entry region, like so. Now, we're going to look at this. Change the temperature of the surface as we move down the tube. In this case, is equal to 0 because it is constant. So, the change of the temperature of the fluid as we move down the tube in the fully developed thermal region is going to be equal to Ts minus Tm over, Ts over T times Ts minus Tm times the change of the mean temperature with respect to X in the fully developed region. This relationship is explained in equation in your text 833, and I'm going to leave it at that for the time being. But I want to show you what the graphs look like. This is Ts. This is Ts. Okay? It doesn't change. What we have in the case of this case is T of the fluid, Tm, looks like this. It is nonlinear. There's an exponential growth. And to answer your question, Scott, that you asked earlier, in this case, no, the temperatures will never equalize. In this case, you make long enough tube, and this will approach this. Okay? Now, there's always going to be some difference in real life because you need some delta T in order to transfer heat. This is the T of the inlet of the fluid. This is the T of the outlet of the fluid. This distance here is known as delta T at the inlet, and this distance here is known as delta T at the outlet. And we will use that in the next lesson, so keep this in mind. Now, in the last couple of minutes, let's take a moment to address the homework problem. Homework problem is kind of fun because you actually get to do some math and you can compare it. Here's what I want you to do. They're floating around here somewhere. Someone send one up to who needs them, kind of? All right. Okay. This is all the same problem, but I've divided it up into two. All right. Saturated water, 300. Use your properties at that. And for those of you who could not find saturated water and last came into my office, it's table A6 of your book. You got a circular tube of diameter .015.